Hello again. This is your instructor Muhammad Hawa. Let's discuss sampling, a very important topic, and also Nyquist rate. Most of our systems today are digital systems. That's why real-life analog signals have to be converted into digital signals to be processed by such systems. I'm not going to go through all the details of analog to digital conversion and going from analog baseband signals to digital baseband signals or even digital carrier signals. Rather, I'm going to concentrate in this video on only the first step of analog to digital conversion, which is called sampling. You'll study more details in more advanced courses. So what is sampling? Let's start with an analog signal, M of t. This is an example of an analog signal. Notice that it's continuous in time and it's also continuous in value, which means you have infinity points on the curve representing the analog signal. Unfortunately, this is not suitable for digital systems because digital systems use ones and zeros. Because I have infinity points, I would require infinity ones and zeros to represent the signal. That's why we say, can we represent this analog signal M of t using a smaller subset of points on that signal? Those points, which we call samples, can actually represent the signal if you pick them carefully. And this is what sampling is all about. Representing your signal using only samples of the signal rather than the continuous time curve. In the process called ideal sampling, what we do is replace the analog signal, this gray curve, with this red curve, which consists of impulses in the time domain, and the area of each impulse is set to the value of the sample of the signal at the location of the impulse. Notice, for example, this impulse has a smaller area because the sample value is smaller. Notice here that this impulse has a negative small area because the sample of the signal M of t at that point is negative. This impulse, on the other hand, has an area of 0 because the value of the analog signal at this point is 0. And we keep building impulses for each sample that are spaced ts seconds apart, where we call ts the sampling time. This is what we call uniform sampling. So in uniform sampling, the spacing between one sample and the next one is constant and it's equal ts. This also gives us the sampling frequency fs, which is 1 over ts in hertz. Or if you want to write the sampling frequency in radian per second, you say omega s is equal to pi over ts. This sampling frequency measures how fast we are creating samples for the original analog signal. A word of caution before I proceed. This process is known as ideal sampling because I cannot create impulses in real life. Impulses go to infinity in 0 time and then come back from infinity. This cannot be built using practical hardware. However, using impulses is quite convenient mathematically speaking, so I'm going to explain ideal sampling. However, you should know that in real life, we use what we call a practical sampling, where we create pulses or rectangular shapes to represent each sample value instead of impulses. There is of course a difference between ideal sampling and practical sampling, but this video is all about ideal sampling because the concepts and ideas that we get from ideal sampling also apply with very little modifications to practical sampling. What I want to calculate here is the Fourier transform of a sampled signal, let's call it x of t, of the original analog signal M of t. If you understand the Fourier transform of x of t, the sampled version of M of t, you'll be able to understand a lot of ideas about sampling. So what is the Fourier transform of x of t, which is a sampled version of M of t? Well, it's easy to see that we can obtain x of t, the sampled version, by multiplying M of t by a repeated delta function, which is known as impulse train. Notice that each impulse here has an area of unity, and those impulses are spaced ts apart, where ts is the sampling time in seconds. if you multiply this signal by this signal, between the impulses you have 0, so you multiply the signal by 0, you get 0. However, at the location of the impulse, you multiply the impulse by the signal, so you scale the area of the impulse based on the sample value of the signal. And that's why the impulses now have different areas, and the one controlling those areas is the original analog signal m of t. If you understand this, then finding the Fourier transform of x of t, which is x of omega, is quite simple. Because what I'm doing here is multiplication in time domain. And I know that the Fourier transform of multiplication in time domain is convolution in the frequency domain between m of omega, which is the Fourier transform of m of t, and the Fourier transform of the impulse train. Let's say that the Fourier transform of m of t, m of omega, is a baseband signal with bandwidth b. So maybe it looks like this. Of course, if I give you a different signal, like a rectangular shape here, the shape of m of omega will be different, and you know that it would be a sinc function. If I give you a triangular shape here, the shape of m of omega will also be different, and for triangular shape in time domain, the Fourier transform should be sinc square in the frequency domain. The important thing is, I'm assuming this signal has a bandwidth of b in hertz, or 2 by b in radians per second. How about the Fourier transform of repeated delta, which is periodic? Well, the Fourier transform of periodic signals is infinity impulses in the frequency domain. I gave you this signal as an example in an earlier video, and I said the Fourier transform of repeated delta of t every ts gives you infinity impulses repeated at omega s, the sampling frequency, 2 pi over ts, and the area under each impulse is equal also omega s, which is 2 pi over ts. Now that you know the Fourier transform here and the Fourier transform here, all you need to do is convolution. And the answer here is quite simple to find, because the convolution of any shape with an impulse gives you the same shape. But you have to scale it by the area of the impulse and shift it by the amount of shift of the impulse from the origin. So if you do convolution between m of omega, this shape, and this impulse, you're gonna get this copy which looks like m of omega around 0. On the other hand, if you do convolution between m of omega and this impulse located at omega s, what you're gonna get is this shape shifted to the sampling frequency omega s. When you do convolution between m of omega and this impulse at 2 omega s, you're gonna get the same m of omega, but this time shifted to 2 omega s. And then you'll get another copy because of this impulse, another copy because of this impulse, another copy and another copy. You'll get infinity copies of the same original shape m of omega. So please understand that you are not changing the shape of the original signal m of omega, rather you're creating infinity copies of that shape located at the sampling frequency, twice the sampling frequency, 3 times the sampling frequency, so multiples of the sampling frequency. Why is this fact so important? Well, because if I tell you now I have x of t is sampled version, only limited samples of the original continuous signal. Is there any way I can go from the limited number of samples that I have here to infinity points again in the analog signal? And the answer is quite clear by looking at the frequency domain. Because if you can isolate this copy around 0 from all the other infinity copies that exist in the Fourier transform x of omega, then you'll be able to recover your original signal m of omega, which is the original analog signal. And we have in real life a device that can do that. It's called a low pass filter. A low pass filter can pass low frequencies below the cutoff and reject the higher frequencies above the cutoff, which means a simple low pass filter will be able to convert the sampled version x of t back into the original analog signal m of t. So hopefully now you understand that sampling means you take a smaller subset of points for the signal m of t. However, you can recover your original signal m of t from those limited set of samples by using a simple low pass filter. However, please, as you calculate the Fourier transform of x of omega and pass it through a low pass filter, be careful about those magnitudes that you get here. Assuming that my original m of omega has a maximum magnitude of gamma, remember that when you do convolution with an impulse, you have to scale by the area of the impulse. So what you're gonna get is gamma multiplied by omega s for each maximum here. But also remember that after doing convolution, you have to divide by 2 pi. So the answer will be gamma multiplied by omega s over 2 pi, which is gamma over Ts, where Ts is the sampling time. So if your low pass filter has a gain of 1, what you're gonna get at the output is gamma divided by Ts. The selection for a value for the sampling time Ts or the sampling frequency omega s is quite critical in sampling. Let me show you where you can run into a problem. Here is a scenario where I picked omega s, a big value. I created copies of the original shape m of omega at multiples of omega s. I can send those samples to a receiver, and then the receiver can use a low pass filter to isolate this copy around 0 from all the other copies to recover the original analog signal. However, if you're not careful, you could end up with this situation where I have a signal m of omega and I picked a certain sampling frequency omega s that is not large enough, which meant I created infinity copies at multiples of omega s that are overlapping. If you create infinity overlapping copies like this, and then you try to use a low pass filter at the receiver, you will not be able to isolate one copy from the rest, which means you will not be able to recover your original signal m of t. This overlap in sampling is well known and it has a name. It's called aliasing. It results in distorting the recovered signal. You will not be able to recover your original signal from its samples. So what is the solution? How can I avoid aliasing? Look at the Fourier transform of x of omega. You'll be able to figure out the answer. What you need is that this omega s to be larger than this interval in frequency plus this interval in frequency, so those two copies do not overlap. This interval in frequency is actually the bandwidth of the signal. And this interval, because of symmetry, is also the bandwidth of the signal. So you want your sampling frequency to be twice as much as the bandwidth of the signal or more to avoid overlap, to avoid aliasing. Here, I was not careful enough and I picked omega s is smaller than 2 times the bandwidth, and that's why the overlap happened. And Nyquist studied this phenomenon and he came up with a Nyquist rate. He says for an analog signal m of t with bandwidth bm, the Nyquist rate, which is the minimum sampling frequency necessary to avoid aliasing, is actually 2 times the bandwidth of the original signal m of t. So to avoid aliasing, the sampling frequency fs that you need to pick should be equal to or greater than the Nyquist rate. Always make sure in sampling you follow this rule. The sampling frequency should be greater than or equal the Nyquist rate, which is twice the bandwidth of the original signal. Of course, here I'm using hertz, but if you want to use radian per second, that's fine too. Make sure that omega s, the sampling frequency in radian per second, is greater than or equal to 2 times w for the message, which is the bandwidth of the message in radian per second, where Wm is 2 pi by Bm if Bm is in hertz. Also, please understand that sampling happens at the transmitter in a communication system, while recovering the original analog signal occurs at the receiver in that communication system. And to recover the original analog signal m of t from its samples, you need to use a low pass filter with a cutoff frequency equals bandwidth of the signal, so the signal can pass through that low pass filter without distortion while rejecting all the other copies that you created from sampling. Please remember that the cutoff frequency of the low pass filter is independent of your sampling frequency, rather it's dependent on the bandwidth of the signal. So let's solve an example. In this example I say an analog signal m of t with bandwidth 100 Hz is to be sampled at 4 times the Nyquist rate. determine the sampling frequency that we are using, and also the cutoff frequency of the low-pass filter used to recover the original analog signal at the receiver. The solution is quite simple. I'm required to sample at 4 times the Nyquist rate. So the sampling frequency is equal 4 times the minimum sampling frequency you can use, which is twice the bandwidth of the original signal. So I need 4 multiplied by 2 multiplied by the bandwidth of the signal, which is 100 Hz. I need a sampling frequency of 800 Hz. If you want to convert that to radian per second, multiply by 2 pi. However, the low pass filter cutoff frequency is independent of the sampling frequency you use and is always equal the bandwidth of the original analog signal. So the cutoff frequency for my low pass filter at the receiver should be 100 Hz, or multiply by 2 pi if you want the answer in radian per second. If you have questions, please leave them in the comment section. This is Muhammad Hawa signing off. Thank you and have a nice day.